Okay. Any questions about the reactions that we had on Friday? One of which was, the last one we talked about was mercuration, demercuration, reacting the mercury acetate and water, and then sodium borohydride. So we had gone through the mechanism of this. Basically, what we have is we have the mercury. When it loses an acetate, it becomes a mercury plus. So in essence, that's what we're adding to the double bond. So we had two possibilities here. We could add the mercury to the carbon, to the first carbon, or we could add the mercury to the second carbon. So we could add the mercury to either carbon A or B, making molecule B an A. And so when we did that, which one did we make? Let's vote. So we're going to add mercury plus to the double bond, and the question is, which product am I going to make? Am I going to make B, which is the one on the top, or A? Which one am I going to make? A or B? Okay. So we're going to add Hg plus to the double bond, and we got 25 to 3 say that we are going to make B as our product. And why are we making B? Because it's a secondary carbocation versus the primary, and we don't make primary carbocations. So then what happens next? Next, the water adds. So the water is going to come in and add to that carbocation. And I'm going to do what I do in SN1 reactions. I'm going to add the entire water molecule to make then the oxonium ion. And then I'm going to lose the H plus to have then added net an OH and a mercury across the double bond. So that's step one. And then with step two, in order to remove the mercury, we add sodium borohydride, which is basically just going to replace the mercury with an H in exactly the same position as the mercury was in. So in the end, I will have net added H and OH across the double bond. Because the H added to the carbon with the most hydrogens, that's going to be Markovnikov addition. So this reagent then, in terms of the three questions, I'm adding H, OH, and I'm adding it Markovnikov. Okay. And that's because I'm adding basically a mercury plus to the double bond. And then the final question was, how does the H and the OH add? And this is where we were at in terms of looking at this reaction. So right now we've looked at Markovnikov versus anti-Markovnikov, which is going to be what we call regioselectivity. And we're going to get into regioselectivity maybe the end of today, but definitely on Wednesday. We're going to go through all those definitions once we've built up a bunch of reactions. So the way I determine how the mercury and the OH added was simply to take something like this and then do that reaction. So I'll add mercury acetate and water, and then in a second step add sodium borohydride. And this is the way the reaction's typically written. So then means it's a second step that's separate. Okay. Now, when we do this reaction, here's what we get. We get the H and the OH added 100% trans. That's what we find, is that the H and the OH added 100% trans. Okay. And that's a bit of a problem, because in the mechanism that I wrote before, I wrote it as an isolated carbocation. Well, if the reaction would have had this isolated carbocation, if that's what forms, then the water is going to add 50-50 relative to the mercury. And that's not what happens. Instead, what happens is the water adds trans to the mercury, because wherever the mercury was, that's where the H was to begin, or where the H ends up. So in this case, the mercury ended up trans to the OH, and then it was replaced with the hydrogen. So what happens in this case is that the mercury is big enough where it will actually sit, or it'll bond to both carbons in the double bond at the same time, and it will make a triangular intermediate. And what also happens then is that the two carbons in the double bond will begin to share the positive charge. So mercury has to be big enough to be able to bond to both atoms at the same time, but as a result then, what we do is what we call delocalize the positive charge over both of the carbons. Now, in this molecule that I gave you, and we'll talk more about this with regioselectivity, it doesn't matter whether I add the H to the top, OH to the bottom, or vice versa, because this molecule is symmetrical. So I'm going to get the same product either way. So I'm focusing on the stereochemistry. And so this mercury then forms a triangle. If the mercury is on above the plane of the ring or below the plane of the ring, what happens is that the water has to come in and it has to add opposite the mercury. So no matter which way we write it, the water is going to come in and it's going to add, let's say it adds from underneath. I'm going to end up with my oxonium ion. That means that the mercury ended up above the plane. So whenever we have this triangular intermediate, the nucleophile has to add opposite it. It has to add from the other side of the plane, which then means that we're going to end up with 100% trans addition. Okay, so we've talked about square. The square of BH3H2O2 was cis addition. The triangle now is always going to be trans addition. Okay. Right. So that's how the stereochemistry is explained. The fact that you form this triangular intermediate and the water has to add opposite it. So the simple fact of the matter is, because I don't end up with 50-50, this can't be a pure carbocation. All right, everybody with me so far? But now what I have to do is now I have to bring the triangle into the context of Markovnikov and anti-Markovnikov. Because when I explain Markovnikov and anti-Markovnikov over here, I just said, well, I'm going to add the mercury to the first carbon, add the mercury to the second carbon, see which one has the more stable carbocation. That's not what happens. Instead, the mercury bridges. So now I've got to take this triangle and explain how we get Markovnikov addition out of that. But I'm not going to do it with mercury. Instead, I'm going to do another reaction, and then we're going to talk about how that happens, because I'm going to use bromine now, and bromine does exactly the same thing as mercury. Okay. So a new reaction is this one. Now let's add Br2 to a double bond. And the first thing that you may say is, well, Br2, I don't see any delta positive or positive species there. You're correct, you don't. But what happens is that when you have the double bond of the carbon, the pi bond, as one bromine comes close to that pair of electrons, it polarizes the bromine so that that part of the bromine becomes delta positive and the other part becomes delta minus. So that only happens when one of the bromines gets close to the pi bond. And when that happens, then they're going to break apart as a Br plus and a Br minus. Now, the way we usually write that in the mechanism is like this. Take this pair of electrons, use it to bond the bromine, and kick the other bromine out as a Br minus. So I end up with doing the exact same thing that I just did. I could say, okay, let's add the Br now plus to the first carbon, or let's go ahead and add the Br plus to the second carbon. We get two different carbocations. Which one is more stable? The secondary is more stable, so we're not going to form this. And then what happens is the Br minus that was kicked out all of a sudden decides to come back in and add. So now I end up with two bromines added across the carbon-carbon double bond. And this is called bromination. So with Br2, my first question is, what am I adding? I'm adding a Br and a Br. How am I adding it? Markovnikov or anti-Markovnikov? Neither. Because I'm adding two bromines. How do I know which one went where? Now that I know the mechanism, I know that the bromine is going to add to the carbon that has the most hydrogens, right, to generate the carbocation. But it just from the product, I got 2 BRs. I don't know which one I added. So this isn't Markovnikov. It's not anti-Markovnikov. Whenever you have a symmetrical reagent that adds 2 things the same, there is no Markovnikov rule. But then the other question is, how do the bromines add? If this carbocation was a pure carbocation, how would the 2 bromines add? If this was a pure carbocation where I've got both lobes being able to be added to, the second bromine, the Br minus, is going to add 50% top, 50% bottom. So if this was a pure carbocation, I get 50-50 cis and trans. Just like the mercury, just like adding H plus H2O to a double bond. Well, that's not what happens. What I find out is that if I take cyclohexene and I add Br2 to it, my final product has the 2 bromines adding 100% trans. So the 2 bromines add 100% trans. So that tells me there is not a pure carbocation being formed. Because if there was, then we would end up with 50-50.
So is that the same rule for the mercury one because of its own intentions?
These 2 reactions go together. The book shows mercury first. I'd show bromine first. It doesn't matter because they both undergo the same kind of reaction. So that's why I'm showing that to you. Except I still have this problem of I'm adding 2 bromines. So yeah, I think the first bromine's adding to the first carbon. I think it's adding like Markovnikov, but I need to bring this triangle into context of Markovnikov, anti-Markovnikov.
How can we tell if the carbocation is pure?
Because if the carbocation was, then the 2 bromines would have added 50-50. So when I come over here, I ended up with 100% trans, not 50-50 cis and trans. So in other words, here's what would if this was a pure carbocation, I would have added the bromine, the Br plus, right? And it would have left that carbon as a plus. So what would happen? How would the Br minus have added? If this bromine was totally bonded over here, the bromine would have added 50% from the top, 50% from the bottom, and I would have ended up with a 50-50 mixture of cis and trans. That is not what I get. What I get is 100% trans. So that tells me that this is not the intermediate. Just like for the mercury, having the mercury attached to one of these 2 carbons and having the positive charge for the water to add 50-50, it's not. The mercury is bridged between the 2 carbons. And the same thing can be said of bromine. It's not this. It's not a pure carbocation. Instead, what's happening is, well, there's only H's there. What's happening here is that the bromine is also bridging delta plus, delta plus. So bromine is forming the same triangular intermediate that mercury is. And that explains why we get the bromines adding 100% trans. That's how we know that the mercury and the water added 100% trans. Kaylee?
I feel like I'm not sure as to why it's adding, like in that triangular.
How it's adding trans?
Yeah.
Or opposite?
Yeah.
Okay. Let me draw it out looking down the ring perspective. So if I'm looking at a cyclohexane ring, sort of as in the ring perspective here, what I would have is I would have my bromine attached to both carbons like that. So this reaction, so if you're a Br minus sitting here, it's going to have to do basically a backside attack. And when it comes in and adds to one of the carbons, then the pair of electrons will go to the bromine, and the bromine will swing to the other carbon. So the Br minus has to add opposite the bromine, because at least as far as a backside attack characteristic, this looks like SN2 from the standpoint of it having to attack from underneath. So when it adds from underneath, then what I end up with is I end up with the bromine down here, and then I end up with a bromine added to the top carbon. Or this bromine added to the top, it's now over here above the plane. This bromine has to add below. It will now be below the plane of the ring.
So does that have to do with when you said that the mercury was like big enough to bond between the atoms at the same time?
So is bromine. Bromine's able to bond to both of those carbons at the same time.
How do you know if it's big enough, I guess?
Because right now hydrogen isn't, but bromine and mercury is. So in other words, if we're going to do these reactions, we've got to take that into consideration. How do I know? Because when I do the reaction, if I end up with 100% trans, 100% trans means triangular intermediate every time. So these two reactions have similar triangular intermediates. I mean, from the standpoint of when somebody did this they probably did bromination first. And they looked at the stereochemistry and they're like, wait, how did I get 100% trans? So then you have to propose a whole bunch of stuff. And the thing you would propose is, okay, well, maybe the bromine can sit on both sides. Then you got to see how big is the bromine. Can it really do that? Okay, let's find another atom that's big enough to do that. Mercury. Does mercury do the same thing? Yes. So this is how the mechanism's been worked out through the years. So right now we just get the benefit of this is how it happens. So bromine and mercury will form triangular intermediates. Does that kind of make sense? So in terms of the stereochemistry, bromine and mercuration always give 100% trans because of that triangular intermediate. Now, let's change this reaction a little bit and make it have the possibility of being Markovnikov or anti-Markovnikov. Because right now, I get two bromines again. I don't know which one added first. I do now that the mechanism's all been worked out, but I didn't know that ahead of time. So in the next reaction, let's do this. Let's take our cyclohexane. Let's put a methyl group here. Bless you. Let's take our cyclohexene. Let's add bromine to it. Only in this case, let's add bromine and water. So we'll add bromine to water, making bromine water. The bromine will be intact to act as the electrophile. So what I'm going to end up doing is I'm going to end up adding my bromine, my Br plus, to the double bond. That bromine is going to allow those two carbons to share the positive charge. The water is going to come in as the nucleophile. We know that the water is going to have to add from the opposite direction of the bromine. And the only question is, where does the water add? That's the only question. So what product am I going to get? Is the water going to add to carbon A, or is the water going to add to carbon B? Now, before you answer that question, let's look at another problem that's a little bit easier to look at. So let's do the same thing with this. Let's do it acyclic. So let me put 2 methyl groups on one carbon, 2 hydrogens on the other. Let me go ahead and add my bromine water to that. I'm going to end up with what's called a bromonium ion. I guess I haven't called this the bromonium ion, but that's what it is called officially. And again, what happens is the carbons can share the positive charge. And I've got carbon A here, and I've got carbon B. So we know the water has to add from underneath. That much I know. So I'm going to get 100% trans. The question is, where does the water add? Does it add to carbon A, or does it add to carbon B in this molecule? Is it going to add to A, or is it going to add to B? No, we're going to vote. We're going to vote. But here's what I'm going to let you do. I'm going to let you discuss for a minute, and then you can vote.
That's why I love it. That's my
Sounds like we're ready to vote. Okay, so I'm just A or B. I'm not necessarily, if you want the option of they're both going to be equally formed, I suppose you could use C. You could use B, or you could use D as, don't know. But is it going to be A or is it going to be B with all the other options? Okay. We have a 16-14 split with one, don't know. Okay. I've been doing this a long time. I can phrase the question to get that split. So, let's think about, or somebody give me a reason for choosing A.
Well, I was thinking that BR is big, so it should be on the side of active substituents, and then there's some arms to it.
Okay. So BR's big. What was your first part?
BR is bigger, so it should
Should move
move over to the B.
over to the B carbon because of what? Steric hindrance? Okay. That's interesting. That's there's very few reasons that I have never heard before, and that's the first time I've heard that one. So That's not saying it's good or bad. That's just saying that's a unique way of looking at it. We're still on A. So we're still on A. Anybody else want to give me their reasoning for A?
I said because it was an 100% chance that kind of went along with the Markovnikov, and you add with the most hydrogens.
So you're going to add what with the most hydrogens? You're going to add the hydrogens to the most water? Or you're going to add the water to the carbon with the most hydrogens? That's B. That's a reason for B. But then that's not Markovnikov. Or Markovnikov, the water would add where? The electrophile adds to the carbon with the most hydrogens, and the water adds to the carbon that's most substituted. So what you described was not Markovnikov, but anti-Markovnikov. Okay, so that's Markovnikov addition. Did we say whether this was Markovnikov or anti-Markovnikov yet? Well, that's good. No, we haven't said that. Okay. Any other arguments for A? How about arguments for B? Annie, you had an argument for B?
Is it for the water or the bromine?
No, the water.
Oh.
You're the water molecule. Who are you going to add to, A or B? Sorry, do we need to, so do we need to rethink our, okay. The vote was still 50-50 though, right? Or do we need to revote? Okay, let's revote. Your choice is, you are the water molecule. Who are you adding to, carbon A or carbon B? That's the question. Your water, are you going to add to A or B? Okay, that's my fault. I screwed up that question. Not where the bromine's going to end up, where the water's going to end up. Okay. We have 26 A's and 5 B's. Okay, so this is the majority answer by a lot. So now let me ask the same question again. Why A? Annie?
So if there's an intermediate form, then you want your intermediate to be on the most stable. You want your positive first on the most stable, and your hydrogen would add to the most
Water. Your water would add to the most. Okay. So let's dissect that. The water wants to add to the most substituted. Why?
Because it stabilizes the delta positive charge.
The charge has something to do with it. So your water, strong or weak nucleophile? Water is weak. What kind of reaction as water are you allowed to do? SN1 or SN2? SN1. Why? Because weak nucleophiles can only react with carbocations. Because your water, you want to react with a carbocation, probably the carbon with the greatest delta positive charge is the way that this will work. It's sort of like we think about SN1 kind of here. So if you're water, you are forced to add to the carbon that has the greatest delta positive charge. You're not tremendously electron rich, but the rules are that all electron rich must give to the poorest of the electron poor. So which carbon has the greatest delta positive charge? I hear A, but it wasn't a very strong A. Which carbon has the greatest delta positive charge, A or B? all but 5 of you said we were adding water to A. So if the water is going to add to A must have the greatest delta positive charge. Do we agree? Why? Why does A have the greatest delta positive charge?
See, because when you want to form your carbocation, you should make the secondary versus the primary. Like when we talk about sharing the charge, it's like one can carry more than the other. So it can make you the carbocation and be the primary.
That's the only thing I'll add to that is it's tertiary. So if you made A a pure carbocation by breaking the carbon-bromine bond, it would be tertiary. If you broke the carbon-bromine bond for B, it would be primary. So what kind of carbocation is this? I'm going to put in quotes that it's tertiary because it's got that partial bond. So if it was a pure carbocation, it would be tertiary. This one would be primary. Which one of those two carbocations is going to be more stable? The tertiary. The methyl groups attached to that carbon are going to be able to let that carbon have more delta positive charge. Now I know those methyl groups are going to feed some electron density into it, but still, that carbon is going to be able to have more delta positive charge than the other one, which is primary. As a matter of fact, the primary isn't going to want any positive charge whatsoever, comparatively speaking. So A looks like a tertiary, B looks like a primary. So where's the greatest delta positive charge going to go? On the tertiary one, A. Okay. Does that kind of make sense? Now, if we did this reaction, if we actually said, well, let's add the bromine to carbon, let's add the bromine to carbon A, let's add the bromine to carbon B, let's write the two carbocations, we would have ended up with tertiary versus primary. We would have X'd out the primary and said, this is going to be our major product because that's where the water would add. So what I'm trying to do here is I'm trying to put the triangle into the context of Markovnikov addition. And why do we even care about that? And the reason we care about it is because the triangle is the real species. If it wasn't the triangle, I would get 50-50 addition. I don't. I get 100% trans, which means the triangle still has to exist. So in this kind of a reaction, because it's water, because there are two positive charges that add up to +1, right? Because the Br plus added to the double bond, Br doesn't want the positive charge, so it just shoved that off onto the carbons, fight amongst yourselves. They do. The tertiary goes, I can handle it, you can't. Or the primary goes, I can't handle this, you can. And it does. And what happens, the water looks up and goes, that's where I got to add because that is the greatest delta positive charge. Now, you can actually see this. So if you, wrong one. So if I was to model these carbocations, these are called bromonium ions when they're the triangular species. The one on the left has two methyl groups. It's perfectly identical. And what you can see here is that you can see that the bromine is sitting perfectly in between the two carbons in the double bond. And that It's because both of those carbons are secondary. Okay. I'm curious about the idea of the steric hindrance, Jenna, because nobody said that, and I could very easily see that being interpreted that way. But it's really because those two carbons have exactly the same positive charge, and so that bromine's going to sit in between them perfectly. And that's the way we write it on paper. And for this one, that's fine. But if I model the one on the right, which is 2 methyl groups and 2 hydrogens, what you can see in this case is that the bromine is actually not sitting perfectly between the two. If we stop it there, the bromine is actually sitting directly above the primary carbon, and it is far away from the tertiary carbon, which is over here. So this bromine is sitting above that carbon. It's sitting a long ways away from that carbon. It's kind of hard to see here, but this carbon, this one, this carbon right here is perfectly sp2 hybridized. All those atoms are in a plane. Whereas over here, you can see that carbon, it's not perfectly sp3 tetrahedral, but it does have some tetrahedral characteristic here. And so what's happening is the bromine is actually sitting over here to stabilize that carbon, because that carbon can't handle a lot of positive charge. So the bromine needs to be there to form a covalent bond with it. Over here, this carbon can handle more positive charge. If it can handle more positive charge, that means it's going to look more like a carbocation being sp2 hybridized, and so the bromine doesn't necessarily have to be there. The bromine's going to be sitting over the carbon that is not going to have as much positive charge. So in a way, this kind of looks like a pure carbocation, except it's not, because the bromine is blocking the top position. So when the water decides to add, it can't add to the top position because there's still a bromine there. It can certainly add underneath. Okay. So in this case, what we have is we have where the bromine goes in relationship to where the charges are. That picture's not in this picture isn't in Top Hat, is it? Something like that with the bromine not sitting 50-50? Okay. No, I'm just curious, because when you said that, I'm like, wait, I'm going to show that picture. So, but it's similar, but it's not, the thing is it's not sterics. It's because the carbon can take the positive charge, it just flattens out. But it's still bridged so that we get 100% trans addition. And this is that modeled, so this is pretty close to real, given all the quantum mechanics and everything else. If my goal was to have these two things printed out on the 3D printer in my office, but I'm a little behind schedule. But these are kind of what it looks like. So you can end up with very easily explaining Markovnikov addition in the context of the triangle. And that's what I'm trying to do here. Okay. The reason I'm trying to do this is because there's a couple other instances that we're going to look at where the triangle comes into play. And one of them is going to continue to be SN1, where I'm looking at the carbon with the most positive charge. But then I could also look at this in SN2 and say, well, wait, I'm going to add to the least sterically hindered carbon and get the exact opposite reaction. But that's not now. Now we're talking about adding the nucleophile to the carbon that has the greatest positive charge. All right, does that make sense to everybody? So this is how we handle a triangle in the presence and trying to explain Markovnikov, anti-Markovnikov. Any questions? I know, it's like, not on Monday, please. Right, it's probably a little too early in the week for this, but it is where it is. So where does the water add? Down here. The water adds to carbon A from opposite the bromine. So what I'm going to end up doing is having my oxonium ion formed, adding to the most substituted carbon, but that oxonium ion is going to be opposite the bromine. So the water comes in, adds, the bromine slides over, and then in the final step, I'm going to lose my H+, and I'm going to form the what is called the bromohydrin. So bromohydrins, when we add bromine and water, or two bromines, we now have those reactions to worry about. So when I add two BRs, how am I adding? Or what am I adding? I'm adding two BRs. I'm adding it neither Markovnikov or anti-Markovnikov. I am adding it 100% trans. When I add my Br2 and water, what am I adding? A Br and an OH. Markovnikov or anti-Markovnikov? Well, let me expand Markovnikov. Markovnikov addition is when you add an electrophile to the carbon with the most hydrogens, and then you add the nucleophile to the carbon that is most substituted. So if I broaden out my definition of Markovnikov, I can now say electrophile add to the carbon with the most hydrogens, nucleophile added to the opposite carbon which is most substituted. The reason for doing this is because Markovnikov's rule says, well, H. Yes, when we started out, what was our electrophile? H+. But now what do I have as an electrophile? I've got a Br+. I've got an HgOAc+. Right? I've got a mercury acetate. So if I start thinking about broadening out the definition of electrophile, I can now call these reactions Markovnikov because those electrophiles are going to add to the carbon with the most hydrogens that are in the double bond. Why? Because that's going to form the more stable carbocation. But what about the last two? They're not forming pure carbocations. Well, the carbon where the nucleophile adds is going to be the carbon with the most electron density, so it's going to be the most delta positive charge, which is basically the carbocation. All right, so BROH, Markovnikov, 100% trans. Okay, for Wednesday, I think we're getting close to the end of reactions here, but we've got a good collection now to talk about. So in your book, they talk about regio and stereo selectivity with each reaction, and if you've been reading through that, going, "What the blank is this?" That's okay. What we need to do is, now that we have a collection of reactions, we can talk about what does it mean to be regio-selective? What does it mean to be stereo-selective? And so that's what we will talk about on Wednesday, as well as I think it's there's hydrogenation is one of the reactions, but we're going to start with regio and stereo selectivity and then talk about those. I'll have the videos into Wednesday's folder by early evening. Okay. If you have questions, put them